Hi, I'm Kirk Sabin, Virtex-7 Product Line Manager here at Xilinx, and today I'm here with Martin Gilpatrick, Transceiver Technical Marketing Manager. Today we're going to demonstrate the capabilities of the Virtex-7 GTH transceiver as compared to the Altera Stratix-V GX device. We've all seen our customers clamoring for 10 gigabit performance over anything from a simple chip-to-chip connection to a difficult multi-connector backplane. The reasoning is clear. The ability to drastically increase bandwidth over the smallest number of pins results in massive performance gains without a drastic increase in board complexity. Of course, this does put a lot of stress on the transceivers, leaving them to compensate for the signal integrity problems these channels can create at such high line rates. Martin, can you talk a little bit about why receiver equalization is important at these kind of line rates?
Absolutely. Backplanes really provide the best example for the problems you can experience here. The channel loss over long trace lengths and the connectors is a large contributor to the jitter observed at the receiver pin. As that jitter increases, the window where a receiver can correctly sample the data decreases, increasing the bit-error ratio and decreasing the effective performance of the link. Over some real-world systems, an eye measured at the receiver can look completely closed. So how can a link possibly work over such a channel? Equalization. Equalization is what allows the receiver to give a boost to those frequencies most attenuated by the channel, thereby removing that jitter that resulted from those losses. In the best 10 gig systems today, there are typically three main components that comprise the equalization circuitry: the active gain control, or AGC, the continuous time linear equalizer, or CTLE, and the decision feedback equalizer, or the DFE. The AGC and the CTLE are analog circuits that first perform a broad amplification, then selective filtering, the result of which is to broadly boost the high-frequency components that the channel filtered out. The DFE takes the result and uses a set of time-delay taps to more finely tune the filtering and achieve the best possible signal for the receiver to sample data from. This description makes getting these circuits set properly sound fairly simple and straightforward, and it's not. Between the AGC, the CTLE, and the DFE, there are far too many settings for a single link to be optimized by hand within a reasonable amount of time. If you consider that any given system could have upwards of 90 plus transceiver links, all operating over slightly different channels, you start to see why hand tuning is not a great option. Furthermore, the channel characteristics and optimal settings can change depending on temperature, voltage, or even the part that you're using. This is where auto-adaptation starts to shine. Having circuitry that adapts the equalization parameters to the current needs of the channel frees designers from having to manually tune each link in the lab, while ensuring that those settings are continually optimized regardless of the system's environment. With that basic outline, let's take a look at what equalization features Xilinx and Altera have included in their transceivers. Active gain control. Xilinx, yes. Altera, yes, but it doesn't auto-adapt. CTLE, Xilinx, yes. Altera, yes. DFE, Xilinx, yes, we have 7 taps of fixed DFE and 4 sliding taps. Altera also has DFE, but only 5 fixed taps. And auto-adaptation, Xilinx, absolutely. Altera, that's been a bit of a question mark. And this is really where things start to get interesting. Altera's receivers are designed to support adaptive CTLE and DFE. However, we've heard from customers that their functionality is far from robust and that they're recommending not to use continuous adapt mode, but rather a one-time adaptation. This means that only at startup do all of the components of the equalization adapt, leaving any changes to the environment to be unaccounted for. To contrast, our GTH transceiver is continually auto-adapting, adapting to any changes in real time. And finally, this is why we're here today, to show you the real-world impact of a fully auto-adapting equalization solution. Kirk?
Thanks, Martin. That was a great overview. So, in order to be able to demonstrate the capabilities that Martin just talked about, we've assembled this demonstration here today. We have acquired a production Altera Stratix-V GX demo board that's publicly available on their website. And from Xilinx, we're using our VC7215 characterization platform for the Virtex-7 690 device. The Altera device is the Stratix-V A7, and it is production silicon from Altera. What we've done is we've connected 4 transceiver links from each vendor over this Tyco Tin Man backplane. The Tyco backplane represents an accurate representation of a customer's real channel that you would typically see in modern wired communications applications today. We've also intermixed Altera receivers and Xilinx transmitters, so we have both vendors' devices acting as aggressors on each other, simulating what you would see in a real-world environment. From a clocking perspective, we're generating reference clocks for both Xilinx and Altera from the Silicon Labs PLL that's on the superclock module on the Xilinx board. It provides a reference clock into the Xilinx FPGA and also into the Altera FPGA. In addition, in each device we have also implemented hammer logic, which utilizes approximately 80% of the flip-flops in both devices. And this hammer logic is used to do two things. First off, it simulates a real-world environment in a real design where you'd have heavy utilization and you'll have a lot of logic toggling in that device. At the same time, that also serves to be able to drive up the junction temperature of the device when that hammer logic is enabled. And you'll see the impact of changing junction temperature on the link margin as we go through this demonstration. All right, with that, we're going to turn over to the tools now, and we'll show you both the Xilinx side and the Altera side up and running here at room temperature, and then we'll apply heat and see what the impact of that is. Now let's have a look at the Altera Transceiver Toolkit software that we use to control the transceiver links on the demo board. Here we have the latest version of Quartus 2 12.1 with device pack 5. And what you can see is that we have 4 links up and running. We're using a PRBS 31 data pattern, and we have the data rate set to 10.3125 gigabits per second and a 644.5 megahertz reference clock. We've set up the 4 different links here in different configurations. The first 2 we've set up with no transmitter preemphasis, and we've set one receiver to one-time adapt and the next one to continuous adapt. This augments a system whereby you may not have the ability to control the pre and post emphasis settings on the transmitter, and the receiver essentially needs to do the work to be able to recover that signal. So channel 0 set up with no transmitter preemphasis, one-time adaptation on the receiver. Channel 1 set up with no transmitter preemphasis and continuous adaptation on the receiver, so we can see the difference between continuous adapt and one-time adapt. Then on channel 2 we have the best transmit preemphasis settings that we could find for this channel, and we have it set to continuously adapt on the receiver. And finally on channel 3 we have again the best transmit preemphasis settings that we could find, and we have it set to one-time adapt on the receiver. So now what I'm going to do is I'm going to go ahead and enable the noise generator that's in the device, and I'm going to do that through this in-system sources and probes editor. What you'll see here is that the device is currently running at a junction temperature of 41 degrees Celsius without the fabric-based noise enabled. So I'm going to go ahead and enable that, and I'm also going to set the power level to the maximum. This will drive the temperature up as quickly as possible, and to further accelerate things I'm going to remove the fan from the device, and we'll watch the temperature rise.
So on the Xilinx side of things, we also have 4 lanes lit up in this design. Unlike the Altera setup though, we have set each lane with really an untuned transmitter. So we have 500 millivolts of swing on each lane and no pre or post emphasis. We're also running that PRBS 31 pattern, and so far have seen 0 bit errors across the board. Now we are using the X80C console within ChipScope Pro to monitor the temperature as well as the Ibert links, but it also allows us to use the Virtual I/O console to enable the noise generator. So I'll go ahead and do that and unplug the fan from here as well.
So Martin, on the Xilinx side, how come there's no setting for one-time adaptation?
Well, we really recommend that you use continuous adaptation, and it works so well that there's no reason to disable it. It works in all situations, and it really just added another thing to have to tune if we included it in here, and you don't need to.
Makes a lot of sense.
Absolutely.
So now let's have a look at the Altera channels. The temperatures come up here now to about 77 degrees Celsius. And if we go and have a look at all of the different links, we look at transceiver link 0 with no transmitter preemphasis and one-time adaptation. We're currently dropping bit errors on that link. We have a look at channel 1, which has no transmitter preemphasis and continuous adaptation. It also has bit errors. We go and have a look at channel 2, which has the best transmitter preemphasis settings we can find and continuous adaptation on the receiver. It has bit errors as well. And finally, channel 3 with transmitter preemphasis settings and one-time adaptation also has bit errors. So all 4 channels now having bit errors on the Altera side. We're currently at a temperature of about 79 degrees Celsius, so I'm going to put the fan back on. We don't want to exceed the maximum device junction temperature, which is 85 degrees C for this particular part. And I'm going to do some eye scans as well now that we're at elevated temperature. The Altera 2D eye scan feature does require that you stop the receiver because they don't have a non-destructive 2D eye scan like Xilinx does. And let's see what these eyes look like now that we're at temperature. We're seeing some significant degradation on the eye, which is kind of what we would expect when we're having significant bit errors. We have a look at the different links. We can see that the eye has collapsed. So here's the Altera 2D eye scan feature in action, generating an eye scan. We are at elevated temperature right now. And as you can see, the link margin has degraded significantly and that eye has collapsed down, which is what's resulting in the bit errors.
Okay, now that the sweep is complete, we can see that it's still a completely wide open eye, very similar to the minimum temperature that we had before. And no bit errors. This is evident really because we don't have a destructive eye scan. This is a non-destructive eye scan, meaning you can scan the topology of the eye without interrupting the data stream. So running it on a real data stream across temperature, obviously, and still have full 0 bit errors and full performance.
Thanks, Martin. So as we've seen here today, both Xilinx and Altera have adaptive receiver technology built into their FPGAs. However, the Xilinx adaptive receiver technology is extremely robust, works across temperature, and is able to compensate for the changes in the environment across this challenging Tycho backplane at 20 dB of insertion loss over a 16-inch channel. What we've seen on the Altera side is that it was less successful at being able to compensate. It was not able to maintain that link margin, and as a result we suffered bit errors on all 4 links on the Altera side. The real takeaway here is that auto-adaptation is required in real-world systems with tens or hundreds of links that you're going to see in a modern comm system. So if you don't have a receiver that's able to auto-adapt, it's going to be extremely challenging to tune that system. It's going to require manual tuning, lots of manual intervention, and special settings for every different permutation and combination on the backplane. It's really not something that's manageable in a modern comms system. So with that, we'd like to say thank you for watching and have a great day.